Hi class, in this recording we're going to focus on more anatomy of the urinary system. Diving in, we're going to focus on renal innervation, the nervous system control of the urinary system. We have a small network of branching nerves known as the renal plexus, and these branching nerves and ganglia are going to wrap around each of the renal arteries. To review, because it's been a while since we covered the nervous system, a ganglia is a grouping of neuronal cell bodies within the peripheral nervous system. And we can see these bulges. Here's a ganglia. At each bulge, here's another ganglia. And a nerve is a grouping of neuronal axons in the peripheral nervous system. And these longer fibers or skinny little branches are the nerves themselves. We find that these branches, these renal plexi are going to follow the branches of the renal artery all the way into the parenchyma or the primary tissue mass of the kidneys, and then they're going to supply innervation to the blood vessels of the kidneys and also to the convoluted tubules of our nephrons, both proximal and distal convoluted tubules. We also find that we have sympathetic innervation heading to the kidney through the abdominal aortic plexus. And this abdominal aortic plexus, when activated, is going to reduce glomerular blood flow. So when we're really stressed out, we've activated our fight or flight branch of our nervous system, we send less blood to the kidneys and slow down the rate of urine production. So there's that stereotype of people being so scared that they pee their pants. And that's an activation of the sympathetic nervous system. So it's not that the kidneys make more urine when you're scared. They actually make less urine when we are scared or stressed out. Our kidneys or our urinary bladders have this tendency to relax the sphincters, making us urinate when we're stressed out. So producing urine in the kidneys and relaxing urinary sphincters are two separate things that are both influenced by that sympathetic nervous system. In our kidneys, if we have less blood flow in our kidneys, we have reduced blood pressure. And in response to that reduced blood pressure in our kidneys, we secrete renin in our kidneys, and that renin can restore our overall blood pressure. But this is going to happen when we have chronic low blood pressure in our kidneys, as opposed to just a little bit of sympathetic activation. Our kidneys also receive parasympathetic innervation, but we don't really know for sure what it does. It's believed that it upregulates urinary output, or urinary production, I should say, but it's not very well established. As we look at the filtrate that's being produced, and how we process it, just to review from the last video I made, filtrate is the fluid that is removed from the blood plasma in the glomerulus. And it builds up in that capsular space between the visceral and parietal layers of the glomerulus. And it's very similar, chemically speaking, to blood plasma, with the notable difference that we don't have protein in the filtrate. The protein molecules are so big they remain in the blood plasma and don't make it into the filtrate. We should not urinate out protein. That's very bad. As we look at the glomerular filtrate, that's the filtrate in the glomerulus, it gets sent to the renal tubules. And then we call it tubular filtrate. And it goes through the proximal convoluted tubule, then to the nephron loop, then to the distal convoluted tubules, and will eventually make its way to the collecting ducts. As this tubular filtrate is moving through the tubes, it is going to have a lot of water removed, and it's also going to have salts and hydrogen ions added as needed to modify the overall chemistry. We find that the cells lining the tubes, the tubular cells, are going to have both passive and active transport as they modify the tubular filtrate. And then this is something that will vary based on the textbook you look at. Since I was taught this way, I'm going to teach to you this way. As the fluid leaves the collecting duct and enters into that minor calyx at the very end of the renal papilla, it becomes urine. So that's the line in the sand. And We just need to, somewhere to define when it goes from filtrate to urine, and that's a really good defining spot. The reality of the situation, though, is it's more of a gradient. Tubular filtrate's very dilute. Glomerular filtrate is very dilute. And then as that filtrate moves through the tubes, it becomes increasingly concentrated gradually until it is urine at the end. Although the difference between the filtrate right here at the end of the collecting duct and right here at the beginning of the minor calyx is really negligible at best. So as we look at the filtrate being filtered in the glomerulus, we are going to have to process the blood plasma and convert it into filtrate. First, we need to have glomerular filtration, where we have the liquid pushed into the glomerular capsules, the capsular space. Then we have tubular reabsorption, when we reabsorb things into the bloodstream. Tubular secretion, when we put things back into the filtrate. So tubular absorption goes from filtrate to blood. Tubular secretion goes from blood to filtrate. And then we have to conserve water. We have a whole lot of osmosis going on to remove water from the filtrate and concentrate the filtrate into urine. So as we look at glomerular filtration, this process of having glomerular filtration is going to involve moving substances past the filtration membrane. We have the endothelium of our blood vessel, then we're going to have a basement membrane that anchors that the endothelial cell to the podocyte cell, or the extension of a podocyte. And then in between those cells, we have these gaps, these slits that substances can travel through. And these slits are so small that blood cells, blood plasma proteins, really large ions, and typically anything greater than 8 nanometers in diameter can't make it through. However, super small things like water molecules, monoatomic electrolytes, glucose amino acids, nitrogenous waste, vitamins and minerals can make it through into the glomerular filtrate. As we look at the filtration membrane, there is going to have 3 overall barriers. The blood endothelium, blood capillary endothelium, is fenestrated. And this is a term we talked about during Unit 1 of this class. Fenestrated capillaries have big holes in the side. So the holes in the sides of these fenestrated capillaries are approximately 70 to 90 nanometers. Pretty dang big, but still small enough to keep blood cells in the bloodstream. So lots and lots of fluid can travel through those fenestrated holes. As we look at the basement membrane, that basement membrane in between the blood capillary cells and the podocyte cells is going to have a bunch of glycoproteins in it. And those glycoproteins are going to do most of the actual filtration. It's a mesh of amino acids and carbohydrates that keeps things 8 nanometers or larger from going through. And because it has an overall net negative charge, it is going to repel blood proteins like albumin and many other charged particles that are negative, have a harder time making it in. It's worth noting, though, that negative chloride ions, because they are so small, can go through. As we look at the chemical composition of blood plasma versus filtrate, blood plasma, the liquid portion of our blood, is 7% protein, whereas filtrate in the glomerulus, or glomerular capsular space, is only 0.3% protein. So overwhelmingly, that protein is going to stay in the blood plasma. And then we have a podocyte, falsely colored here as a purple cell in this electron micrograph. The podocyte is going to have extensions coming off of it, and these pseudopods coming off of it are the foot-like extensions that help to improve the quality of this filtration membrane. Those foot-like extensions are referred to as pedicels, and they'll wrap around the capillaries of the glomerulus and have approximately a 30 nanometer filtration slit. And these just serve as an additional layer to help maintain the filtration membranes. Now, as we look at, give me 1 second here, later, remind me tomorrow. All right, so as we look at those molecules that are really, really tiny, anything pretty much less than 3 nanometers in diameter can go right through the filtration membrane. And it includes all of these things which we've previously mentioned, notably ATP. And ATP normally is not going to be free floating in the blood plasma unless something weird's happened, like there's been a crush injury, or you have lots of tissue lysis, where tissues are spontaneously lysing all over the body and dumping their cytoplasm into the bloodstream. But that's pretty rare. I mean, it occasionally will happen. So if somebody has rhabdomyolysis, for instance, it can happen. But usually that's considered a pathology. As we look at very low molecular weight substances, they'll sometimes be stuck to a plasma protein and not make it through. So calcium ions, iron ions, thyroid hormone, by themselves they'd be able to go through the membrane, but because they are stuck to a plasma protein, they can't make it through that membrane. As we look at our kidneys, if we have trauma to the kidney or some kind of an infection to our kidney, we can have abnormal urine produced. A huge big red flag is if you have red urine. And that's known as hematuria, or when we have blood in the urine. And hematuria can be minor, so you could have microscopic hematuria where you don't actually really see the red coloration, but if you look at the urine under a microscope, you could see erythrocytes. Or you have gross hematuria when you can see the pinkish red color of the urine directly. We also could have protein, particularly albumin, make it into the bloodstream. And that's known as proteinuria when we have, or I should also say albuminuria, when we have that protein build up in the urine. It is possible to have proteinuria or protein in the urine, but not blood cells. If blood cells are making it into the urine, it's also assumed that the smaller protein molecules are also able to make it into the urine. If somebody's working out really hard, maybe they are a distance runner or they are a competitive swimmer, they might have temporary proteinuria or hematuria because that prolonged strenuous exercise is going to reduce the perfusion of the kidney, causing the glomerulus to partially deteriorate with prolonged hypoxia or low oxygen environments. And consequently, you can have some fragments that normally won't make it into the urine, make it into the urine. In particular, distance runners occasionally will have elevated ATP concentrations in their urine as well if they've had a hard workout day. For the 12 hours after that hard workout, occasionally you'll see elevated ATP in the urine of those distance runners. That's all we have for our recording. If you have any questions or comments, please feel free to post them in the class discussion board or to shoot me an email. And as always, happy studies.